Good afternoon again. We're continuing our discussion on gravitation. General relativity is what we're heading towards. I will actually head towards quantum gravity eventually. I'll show you how to use some of the principles I'm showing you. In other words, when we get to the curvature tensor and things like that, how to implement that in quantum field theory and make it curved space. That's a long story. Or even just quantum mechanics and include gravity. I don't believe gravitation as a force will ever be unified with the electric force, the magnetic force, call it the electromagnetic force, or the nuclear forces. I don't believe that because they are forces pushing and pulling. Gravitation is not a force, it's a fictitious thing. The force that I experience when I stand on this floor is very much like centrifugal versus centripetal force. It's the way I view it. Other people might not. There's no force. The only force, I'm on the 6th floor. The reason I'm not falling to the 1st floor is because there's a floor underneath me. There's an acceleration. My normal world line would be to direct me straight down towards the center of the Earth. My normal world line in orbit would be just some kind of ellipse if it was a closed orbit or a conic section, whatever. The normal world line right now is just, since I'm not moving, actually I'm moving, I'm rotating with the speed of rotation of the Earth, so slightly. Okay, it's straight down to the center of the Earth and then back up again. It would be simple harmonic motion if it was a huge well between here and the other side of the Earth. Simple harmonic motion is what I would execute. Anyway, we're talking about general relativity, and the last time we talked about contravariant and covariant components of a vector. Well, we specifically looked at a vector, but that's just a tensor of rank 1 because it has one index. We put the index upstairs to denote the contravariant components and downstairs to denote the covariant components. I'm going to take my time with this one because I tried to cover a lot of ground in the previous ones because I wanted to do some calculations. So the vector a mu, or a nu, whose components are that, is a tensor of rank 1. Now, how do these components transform? What does transform mean? It means you go from one set of coordinates to the other. Actually, I'm not going to write it that way. All right, we will. So that the transformed components are functions of the old components. So if we started off in polars, how do we get the Cartesians? That's the way we do it. And this is what the equation looks like in our notation. This is a specific case. All right, so then how the contravariant components transform under general coordinate transformations. That's what tensors are all about, by the way. General coordinate transformations. Because what you wanted to do when we started off with this business, we wanted to get from flat Minkowski space to a curved space. Okay, so the old coordinates, a mu, contravariant and covariant, transform like this. Upstairs, upstairs. They are functions like this. This one, okay? Now we have to sum over something, so we sum over these guys. This is a one free index. We sum over the two components. So for example, in this case here, we go the x dash by the r, this is the x dash, and the x dash by the theta, a theta, ar, okay? So, the way the vector transforms decides what kind of a one it is. Now we did an example in the last case. We did, I don't know why I did three-dimensional case, because you know, when you want to teach something, you want to keep it simple, keep it small. I did a three-dimensional transformation calculation the last time. I made a mistake and I'm going to correct it in the next lecture. Okay, so tensor of rank 1 is a vector. How does the covariance situation look? Well, we go downstairs. The free index is downstairs. And we look at the inverse functions. X nu, right? And we sum over these. Sorry, I'm not doing this right. Let's do the nu. We sum over the free index nu. I don't know why I put a mu up here, it doesn't matter. And the free index nu and the summation index, sorry, nu. Some people call these summation indices dummy indices. I don't like that, there's nothing dumb about them. Now let's look at, oh yeah, by the way, a scalar, it transforms, doesn't. It's an invariant. From one coordinate system to the next, it has the same value. Now, a scalar function churns out a number, right? What's the value of the number? Some function of x gives me a y. Now, it could be the length of a vector, it could be anything, it could be a temperature. One way or another, if we transform to a new system, we will get a different kind of a function maybe, using the different coordinates, the transformed coordinates, but the number has to be the same. For example, if we have the length of a vector, here's one coordinate system. In the xy system, a vector will have a certain length, call it L. In the rotated coordinate system, it has to have the same length, otherwise there's something wrong. Okay, so that's what we're talking about. Transformations, contravariant and covariant components, in this case of a vector. We'll move ahead now to generalize it to tensors of any rank. Let's look at the metric tensor first. G mu nu is what guys say when they go to a relativity conference. Finally figure that one out. So the metric tensor G mu nu transforms like this. Where do we put the dashes? For each covariant index downstairs, we hit one. And we hit one. Okay? And what are we summing over? The mu's and the news. And I have a big example I could do that, but it's YouTube. You know, I might direct you guys to look up calculations elsewhere to save time, and I'll give you the big picture. Sometimes I'll do a calculation, but you know, it can be tedious and people don't watch it. This is the way a rank 2, the G mu nu tensor is a tensor of rank 2 because it has two indices. So we're summing over the mu's and the news, and these are the free indices. So the G11 let's say gxx or just the gxs tensor. And it's a dashed. It's a new one. It's a transformed one. But we sum over the other ones. So we go through all the various possibilities. Well, actually, let's simplify the case. Let's stick with what we'll call a diagonal metric. And we'll look at a diagonal metric, in general in a minute. Okay, so a second rank tensor transforms just using the derivative of two separate of the functions. This is covariant, and what way do you think the contravariant one is going to go? You guessed it. Just like the vectors. Now, the contravariant version of the G mu nu tensor is given by the matrix of the cofactors of the G mu nu downstairs over G. And we call that G mu nu inverse. Okay? G is the determinant of G mu nu. Now that means you guys have to go away and look up determinants and matrices. It's a prerequisite actually for all this stuff. Okay, so, all right. Go through a general coordinate transformation. That is one set of coordinates, and how does it look? This tensor look like in another set. I put in our mu's and our nu's. Upstairs are the dashed, so they go upstairs. They're the inverse functions of the previous, and summed over these indices, so that the free indices are the mu dash and the nu dash. I don't say dummy indices, but the summed over indices are these two ones. And for a diagonal metric, it will be like this. For a diagonal metric, it would just look like that. Okay? So far, so good. If there were off-diagonal elements, you would just go 1, 3, 3, 1, etc., and all the other possibilities. Okay? That's how the metric tensor transforms. Now we consider a set of transformations The new coordinates are going to be functions of the old coordinates, and that's what we're using all the time. And we use that kind of a derivative. Now, for the contravariant components, we used functions of the old coordinates. For the contravariant case, we use functions of the new coordinates, okay? And we sum them over, multiplying by the terms. That's really what we were doing in the previous two examples. It could be. Never mind, that's basically it. All right, so let's look now at what we can do with the metric tensor. Taking those functions, let's look at dx mu over dx nu. Well, these functions are only functions of the x mu's. So if I introduce x mu's, if there are no x mu's in here when I take a derivative, this result is 0. So we'll say that this result is 1 when mu equals nu. Just take a derivative of a function with respect to itself, and it's just 1. And this one here, when mu dash equals nu, okay, hold on, dash, it's also equal to 1. So it's equal to 0 otherwise, and what is that? Well, we know what that is. It's the chronicle delta. We get the chronicle delta using this derivative, okay? Chronicle delta is a powerful tool. Now, can we get from a covariant tensor to a contravariant tensor and vice versa? We can, using the metric tensor. We're going to memorize this and derive it someday if I have time. But right now I'm just going to quote it as a result. Summing over the mu's and having free indices of mu and lambda gives me the Kronecker delta from the product of the metric tensor. Summing over the mu's, one index downstairs brings the index of a vector, a nu, downstairs. So I get from a contravariant to covariant component for that vector a mu. Similarly, I can raise the index. Let's see if I can lower one of these indices. That's the way it works. Let's see if I can lower both. one hits the mu, and this one hits the nu. Now, an important result is that the metric tensor is symmetric. G mu nu is G nu mu. Now, for the diagonal case, a diagonal metric might be A, B, C, D. The contravariant form of the G mu nu, whose elements are diagonally A, B, C, and D, is the matrix of the reciprocals. So, only for the diagonal case, is a matrix of the reciprocals. Yeah? This is only for a diagonal case. And then there are many other things that we can show for simplified results for a diagonal metric. We'll do that later. Let's do a mixed tensor. Here's a rank 4 tensor. Actually, it will be the curvature tensor later on. Now, if we transform to a new frame, we have two indices, contravariant, two indices, covariant, and we get this. We have a product of 4 different functions times the old matrix. Now, I use indices mu and nu dash. They're different indices. A lot of people shy away from that. So we put the mu's and the nu's in first, and we put the rhos and the sigmas in next. And we need to sum over these ones. And that's the form of a mixed tensor transforming from one coordinate system to another under a general coordinate transformations. That's a function, that's a function, that's a function, that's a function, and that's a product of 4 of them, and it can be quite complicated, obviously. Now, don't forget, if we have coordinates and we look at covariant components, how are they related? We'll take the tangents. Let's look at this. These two straight, locally Cartesians. We'll take a point here. We said this before. That's how covariant components get measured. I would say this is the position vector. What do the contravariant components look like? we look at the same triangle and the same point, which is the tip of the position vector, we measure components parallel to x1 and parallel to x2. To get the countervariant components, right? And then it becomes a mess seeing how this works. That's just good enough for us for now. Now what's coming up next? What's coming up next is a little bit of calculus of variations in this stuff. We're going to look at geodesics, the shortest distance between 2 points in a space. These shortest distances are crucial because they turn out to be the equations of motion. They turn out to be the way objects move into space, and it's no coincidence. Because when we had Lagrange's equation, when we're doing classical mechanics, we write down a Lagrangian, which is the difference between potential and kinetic energy, and we minimize what's called the action. Now that means that we take a point in space, right? The system evolves such that the difference between the potential and the kinetic and the potential energy is a minimum. Let's take a spring, for example. What's the condition that this is the minimum? We apply Lagrange's equation. The path between A and B is made into a minimum using, by nature actually. And what's that? Well, we go apply Lagrange's equation. Apply Lagrange's equation, minimize the path for us. So dl by dx dot for this one here is mx, sorry. d by dt dl by dx dot, sorry. mx double dot, now what is a dot? X dot is a velocity and x double dot is an acceleration. Now what is dl by dx? It's just this. So we get minus kx. So d by dt, dl by dx dot minus dl by dx. Now I might have a sign wrong here. Ah yes, negative times negative dl by dx is a negative dl by dx, so it's going to be a positive. And of course it's a spring, we get Hooke's law for a spring. Now this is basically, this equation here is a geodesic equation. It gives me a geodesic from the mechanical system. In general relativity, this is a geodesic equation. Or at least it's one form of it, and we'll get to that in a minute. That's enough for this particular session. I always run out of YouTube time.